Right, grade 12s. What I want to just revise quickly is the exponential function and the log function. Now, if we just do a few basic examples of this, have a look at this. If I take a graph from last lesson, something like this, y is equal to 2x. We call this an increasing graph. It's going, as you move from left to right, it increases. And you'll notice that the base is actually a number that's bigger than 1. In fact, it always works as if your number is bigger than 1. So if we take any graph like this, a to the x, the base a must be bigger than 1. I'll explain why it's not equal to 1. If you've got a graph that does this, it comes down like this, it's decreasing from left to right. It's normally, and without getting too technical, your base will be a fraction, but that fraction is restricted from 0 to 1. Okay, it's going to be like a half, a quarter, or it can be there. If your graph, if you say, for example, if your base is equal to 0, so say you had 0 to the x, or you had 1 to the x, if your base was 0 to 1, these guys are no longer exponentials. They're in fact horizontal lines. So we always say that if the base a is bigger than 1, it's an increasing graph like this. If your base is a fraction between 0 and 1, then what happens is that the graph decreases. Okay, remember both graphs cut at 1. Okay, so when you now bring in the inverses, which of course are the exponentials, if you have a look at this, there's some very interesting stuff that happens. When you've got a graph like y equals 2 to the x, remember its inverse works like this, and that was x is equal to 2 to the y, which is the same as log x to base 2, which is y. Now also something worthwhile knowing, because the restrictions on the base are either bigger than 1 or a fraction between 0 and 1, there's another restriction with the log graph, or the inverse of the exponential, is that you'll notice that the x's are always positive. Your x, you never go beyond to the negative side. The x's remain positive. So there's some restrictions for this. Also, if you take so in other words, for the log graph, your x's are going to be positive. So if you take any graph that's decreasing, say we take the decreasing graph here, which would be, say, y is equal to a half x, where your base is a fraction between 0 and 1, your log graph would look something like this. X is equal to half to the y, but this is the same as log x to base a half is equal to y. Okay, now, the important thing with this is that, again, your x is bigger than 0. Your log graph is always to the right of the y-axis, where x is positive. Okay, so we need to really summarize all these things. So if we look at all of this, if we kind of summarize this now, because we need some theory before we develop logarithms. If you've got increasing graphs, okay, let's just revise this quickly. Increasing functions, what they do is the exponential, as you move from left to right, it increases like that. And this would be the graph of y equals a to the x. Okay, or if you look at the log graph, which is the inverse here, that also is an increasing graph as it moves up from left to right. That's log x to base a. Now there's certain restrictions. Your a in this case is bigger than 1 in this case. Alright? In other words, your base is bigger than 1, like 2x, 3x, 3 to the x, that kind of thing. And also for the x must be positive when you're talking about the log graph here. Okay, so these are conditions on the log graph. Okay, the other thing is if you've got decreasing graphs, let's write them down. The decreasing graphs would be, of course, if you have a decreasing exponential, it goes down like that, and it's decreasing, it goes down from left to right, and it would be y equals a to the x, but your base is a fraction between 0 and 1. You can never be 0 and 1. And in fact, I'll show you something else that's important as well. When you go like this is the log of x to base a, where your base is a fraction between 0 and 1. And again, your x is positive. The other thing, just watch out, your base, a, can never be negative. A is never negative. It's the graph will never be exponential. It's actually a weird graph. So you'll never have something like this. negative 2 to the x. That's not allowed, because if you plot the graph, it becomes very weird. You can actually check that, in textbooks and that, but we never allow it to be negative, because this graph would be all over the place. It's not a fixed graph. It's very difficult. I'm not going to draw it, but a is negative. So if we summarize some important theory for logarithms, for the expression, if you take log x to base a, okay, the most important thing on the a, you only allowed to be noughts, between noughts and 1, then you're decreasing, or you can be greater than 1. Any number bigger than 1. You're never going to be, a cannot be equal to 1, and a cannot be equal to naught. And a cannot equal a negative number either. So you can't have the base being negative, 1, or naught. And also there's a condition on x. The x must be bigger than naught. It must be positive because of the nature of the graphs. If you look at them, this graph here is strictly to the right of the y-axis where x is positive, and likewise for this one here where your log graph is to the right, x is positive. So these little conditions are extremely important when we deal with logs, and I want you to hold on to that, okay, and we will refer back. So with log x to base a, you're only allowed to be a fraction between naught and 1, bigger than 1, and this x expression must be positive. Okay, your x's are always positive there. Okay, now a typical example that they could ask you, if we extend this a little bit here, what we're going to do is I'm going to give you, let's say for example, f maps x. They often use this notation, and they say log x to base a, and they give you a point on the graph. Okay, now if you look at this is the same as y equals log x to base a. It's really just another way of saying y equals. And they asking you in the first part of the question is determine the base a. Well, we know that that is x and that is y, so we can substitute the points in. So y becomes negative 2 is equal to log x is 4 to base a. Okay, what a pleasure. Now, if we apply the definition of a logarithm, if you remember what it was, if I said to you, if you look at this, if we had, say, for example, let's have a look here, x is equal to 2 to the y, say, for example. Remember that became log x to base 2 as y. So likewise, if you had, for example, you could reverse it this way as well. So if you had y is equal to log x to base 2, you could reverse this, and the 2 goes up and pushes the y. You see that there? So you get it back into this form. So what we do with this, if we remove the log, the a kind of pushes the negative 2 up, so you get a to the negative 2 is equal to 4. Remember, if x is 2 to the y, then log x to base 2 as well. It's almost as if the 2 is gone and become a base on the other side. If you've got this here, what do we do? This is the base, so we move it up and push the y up. 2 to the y equals x, and that's exactly this. So once we've removed the log, no problem. Okay, now this is 1 over a squared. Okay, no problem, because we're dealing with the negative exponents. Let's cross multiply, or multiply by the LCD, or we multiply both sides by a squared, and of course the a squared shoots up there. Then of course what can we do? Divide both sides by 4. But now remember, when you solve this, you'd normally have plus minus, so you would say plus minus a half is equal to a. But of course remember, your base a can never be negative, so we say but a cannot be negative. Okay, because of the fact that's the rule of the base, so therefore a is equal to a positive. That's a fraction between 0 and 1. Remember those conditions regarding there. You cannot have a being negative. Okay, so remember, the important thing is to remove the log. The a shoots up and pushes negative 2 there, like it does over here. Or remember the definition of logs. There it goes. Here we go. Look at this. If x is 2 to the y, then y, it pushes the 2 down, in other words, and it becomes log x to base 2. So watch out that movement, that using that log definition. And then of course what we could do is we want the equation, which would be then fx is equal to log of x to the base a half. And that graph, if you remember, is a kind of a decreasing graph doing that. Okay, It's the inverse of that exponential there. Okay, now the next question says you've got to write down number B, the inverse, of this graph here. So what do we do? Let's just go up a bit here. We can say, well, look, if this is the graph of f, okay, if that's the graph of f, well, how do we get the inverse? Well, we interchange or swap the x and the y around. Look at that. And then if we do that, that's no problem, because what we can then do is we can remove the log. The base here goes up and pushes the x up, and you have an exponential graph. So what is the inverse of the log graph? Is the exponential, the little decreasing graph like that. Okay, so what a pleasure. And they could then ask you to draw neat sketch graphs of the log x to the base half and its inverse on the same set of axes. So how would we approach that? Let's have a look. Okay, what are the two graphs that we're going to sketch? The one is going to be the f graph, which is going to be the log x to base a half, and the other one is a half to the x. Okay, that's the f, and that would be the inverse of that graph. Okay, now there's many ways you could probably approach this as well, if you like. If you want to get x on its own here, you would just simply say, well, the half pushes the y up, and we're left with this. In fact, you could even sketch this graph and then do this one. But if we did start with that, how would we do? Let's check it out. Okay, so if we've got x, if we've got that there, we've got basically x is equal to, I'm going to rewrite it like this, a half y, and then you've got y is equal to a half to the x. Well, what we could do here is if you take some values here, you could select values for y if you wanted here, which we can choose -1, 0, and 1, and then look at what the x is. Well, what's a half to the -1 is 2, half to the 0 is 1, and a half to the 1 is a half for this one. Now, if you look at this, if we choose x values here of -1, 0, and 1, what would the y values be here? Half to the -1 is 2, half to the 0 is 1, and a half to the 1 is a half. Now, notice you'll see that there's an interchange of x and y. So if we then draw these graphs on the same set of axes, what do we have? Let's have a look here. I'm going to draw this graph. Let's start with the log graph. Okay, so there's -1, and we go up to 2, 1, and we go down there. So if x is 2, y is -1. If x is 1, y is 0. And if x is a half, the y value is 1. Now this is your log graph. It's decreasing. It comes down like this. There we go. Okay, and I'm just going to put the points nice and thick on the graph there, so that I make sure that the graph goes through those points. So that's the graph of the log one. Y is equal to log x to base a half. Now what about this exponential? -1, 2. If x is 0, y is 1. And if x is 1, y is a half there. So this graph comes down like this. You can see that is your logarithmic graph. It's the inverse. It's a half to the x. Now look at that. Isn't that amazing? It's a beautiful concept, this. Okay, so really you're given a point on the graph, and you then you work out what the equation is, and there you go. And you've got that there. So remember, that's so important that when you take the exponential graphs, for example, the decreasing graph that goes down like that, so that would be y equals like 2 to the x. The log graph goes like this. It decreases log x to base in fact, that's a half there. If we keep it as a half there, and that will be a half. That'll be decreasing there, you see. So, and remember, if this is 1, they both cut at 1. Then you've got the increasing graphs. If you've got an exponential doing this, now notice the base is bigger than 1. The log graph does that. Again, both cutting at 1. Y is equal to log x to base 2. You interchange that. So how did I do this? I said x is equal to a half to the y, and then you introduce the log notation, which gives you the log function there. Okay.